All right, so we'll continue on graph isomorphisms, and I will talk about the walking around in a graph. Okay, so last Monday we discussed the notion of a graph isomorphism to capture the two graphs actually have same structure. The only difference is their drawing may be different. So that's the meaning of graph isomorphism. All right, so we have a bijection. So of course, these two graphs have same number of vertices, so it's a bijection. Each vertex will map to in G1 will be mapped to a vertex in G2, a distinct vertex in G2, so that adjacent relation is preserved. So that's what means V1, V2 at the edge in G1, then their image F1, V1, V2 is also an edge. So they preserve edges. All right. So when two graphs there are isomorphism from one graph to another, we say these two graphs are isomorphic, and we use this notation to denote these two graphs are isomorphic. Okay, there are a couple of things I want to point out. One is this notion, as I explained earlier, captures that two graphs actually have same structure. The only difference is their drawing. All right. Now, secondly, so why do we need that two graphs the notion of isomorphism between two graphs is because when two graphs are isomorphic, whatever is true for G1 remains true for G2, as far as the statement has nothing to do with vertex names. It has nothing to do with vertex names. So once we know the results for G1, then we can apply these results to G2 as well. No need to do it on G2. For example, here there are 5 different drawings of the famous Peterson graph. All right. Now, for this drawing, it's not difficult to see that this graph contains 12 5 cycles. So this one contains 12 5 cycles. It's not difficult to find out in this drawing. But in these drawings, it's not easy to determine number of different 5 cycles. But once we know this graph is isomorphic to each of them, all of them are same graph actually, but just different drawings. Then we can say this graph has 12 5 cycles. All right. Similarly, this one has 240 Hamiltonian paths. We may discuss it about Hamiltonian cycle and Hamiltonian paths later, but does not matter for time being. It's just a property. So this graph has 240 different Hamiltonian paths. So once we know this, we can say that this graph also has 240 different Hamiltonian paths. Similarly, this one has 120 automorphism, then all these graphs, each of them has 120 automorphism. Okay, so isomorphism allows to treat G1 and G2 actually the same graph. They have same structure, same graph. Okay, so it's quite useful because once we know the results for G1, then we can use these results for G2 directly. Third, this relation is an equivalence class, equivalence relation. So therefore, we can use this relation to classify graphs into different isomorphic classes. So we can classify graphs into different isomorphic classes. In each class, these graphs are isomorphic. All right. So these 3 important points I want to emphasize. And fourth one, isomorphism actually means we can reordering vertices of G1. So that after this reordering, then we get graph G2. Then G1, G2 will look exactly the same. So I will give you an example, okay? Then I lead to 5th point. So let me give you a little bit more detail about the 4th point. Okay, I give you 2 graphs. Okay, that's one graph. That's another graph. Okay, all of them have 5 vertices. All they look totally different, these two graphs. But actually, these two graphs are very same graph, but with different drawings. So let's see. So for example, for this graph, let's say maybe let me label it this way. Starting. Yes, I give them names. Okay, so this graph I will also give them name. Maybe V1, V2, V3. Okay. Now, so I want to draw graph in a kind of canonical form. So one way to do it is odd vertices on a line. So this one I odd vertices on line. I have V1, V2, V3, V4, V5. So in this way, okay, just following this ordering, using ordering of names, I can draw a graph. All right, now, so here I can see that V1 connects to all of them. V2 to 3 and 5. 3 to 4 and 2. And 4. So I have this drawing in linear fashion. Okay, now if I draw this graph, I want to use different names. Instead of V, I may use U instead of V. All right. So I draw again. I follow this ordering. I draw this graph. Right. So U1 is adjacent to U2 and U5. So U2 and U5. All right. U2 is 1, 3, 4. 1, 3, and 4. 3 is 4, 5. 1, 2 is there already 4, 5. And 4 is 5. All right. Once we arrange vertices in a line and draw it in this way, so it's canonical drawing. So it's a kind of standard way to draw graph. For example, we do it in this way. All right. Now we can see these two drawings are totally different. All right. However, I can reordering vertices in this graph so that this drawing will be look exactly the same as this drawing. So ordering actually determined by isomorphism. What happens is for this one, it's quite simple. I just V3 will correspond to U3. Isomorphism is a bijection, okay? So actually, V3 will be correspond to U3. Okay, maybe I give you reordering first. So what I will do is reordering vertices. Only change this one. Move this one here. All right. Oh, okay. It's going need to. I change the two actually. This one D2. This one also needs to be moved. All right. So that means now then V3 will be first vertex. V4 will be second vertex. Then okay. Let me see. So the ordering will be V3. All right. V1. Then V4. Then V2. Then V5. I have to do all the birds in this way. Then I draw the graph to see if I indeed we get the graph. I found oh, so this location is wrong then. Should be in the middle. So this one should be in the middle. This one should be here. Four. All right. I missed the one here. I missed the one link. Here, one link is missed. So look like this. So I forget this edge in this part. Okay. So that's what B1 is adjacent to all of them, right? So this one moved in. B2 is 4-3. B2 is it's a 5-5-3. So let me see the ordering. Now let me redo it again. Okay. Let me maybe give isomorphism first. Otherwise, get confused. Okay, so originally this one 1, 2, 3, 4, and 3, 4, 2, 3, 2, 3. So look like this. There are automorphism there. Okay, so let's see. So what happens is there are isomorphism between this graph and that graph. One way is B1 corresponding to U3. So that's one U3. All right. Now, actually, these are not really matters. It's so one way is so this one is 1, 2, 3, 4. U2. So that will give us isomorphism. So it's U3, U1, U2, U4, U5. So that's correspondence between VI and UI. All right. Now what happens? So I want this one to be this one. So U1. So the ordering will be E2, U2. All right. So that's ordering U1, U2, U3, U3, U4, U5. So here U1 will correspond to V2, U2 correspond to V3, U4 correspond to V4, U5 correspond to V5. So I have this ordering. All right. Now according to this, to draw this one. So V2 is adjacent to five. All right. So 3 is 2, 4, 1. One is all of them, and 4, 5. So now once I reorder these vertices as this, in this particular ordering, I get this graph. So the isomorphism, their bijection. So using that bijection, if I follow order, I redraw the graph. So reorder vertices, I get this ordering. Then these two graphs look exactly the same. All right. So what does it mean? Reordering means a permutation. The permutation of vertices. Once I commute the vertices, then it looks exactly the same. The only difference is their name are different. Right. Now, in terms of linear algebra, that means there exists a permutation matrix such that this one, when I transform this matrix by exchanging rows and columns, then I get the second matrix. So permutation matrix, when I use it to multiply to a matrix, it changes rows, commute rows. When I multiply its transpose, multiplied by right side hand side, it's exchange columns. So what means is in common adjacent matrix, if I change the row and the columns simultaneously, and then I can get adjacent matrix of A2. So that meaning is we can get A2. All right. So that's the meaning of isomorphism. Actually, it's a really exchange rows and column in the adjacent matrix, then we get A2. All right, and make a comparison to enforce the idea of this one. Make a comparison with system of linear equations. Then you will see what I mean. Okay. Consider a system of linear equations. Consider this equation. It's a system of linear equations. All right. Now consider another system of linear equation. So what can we say about these two linear system of linear equations? Obviously, you will say the same equation. The only difference, I exchange these two rows. So here I exchange them. Second row becomes third row becomes second, right? That's the only thing happens. So whenever we know how to solve this one, we know how to solve this one. So in terms of matrix, this one, in terms of matrix, right? So this one is but ignore this part for time being. Okay. So typically in Gauss elimination, we'll use a dividing line. See the coefficients is this number here. So basically look at this matrix. So these two matrices, actually same matrix. The difference is we there are no exchange. So they are swapping between two and second and third rows. All right. So basically the structure of these two matrices, if we ignore this part, they're really same matrix, but we have a low exchange. All right. Now look at this one. This one, and again, whenever we know how to solve this matrix as this equation, we know how to solve this one. The only difference is we exchange these two columns. In other words, the name of the variables, here is y, here is z, so here is y, here is z. That's the only difference. So corresponding to matrix, what happens is so we exchange these two rows, these two columns, to get another matrix. All right. So in terms of solving system and linear equation, actually all of them are same. Just matrix has same structure. The only difference is we exchange the columns and rows. That will not affect our solution at all. So if you understand this one, then you can use this idea to explain how the isomorphism works for graphs. So what we do is swap row in the column or make one adjacent matrix simultaneously to get matrix of another one. All right. So this is the other one matrix. For example, we have so for example this matrix. So we exchange some rows. Now when I swap ith row and the column, by changing them simultaneously, we must swap these two columns simultaneously. All right. So isomorphism means in terms of adjacent matrix, we can do this so that the first adjacent matrix becomes the second one. So that's the idea behind isomorphism. All right. When we look at matrix point of view, what happens is swap row and the columns, so we get another matrix. Okay. I have to mention that isomorphism problem is extremely difficult. It's a classical problem and very, very fundamental, very fundamental, but it's very, very difficult. I give you two graphs. How can we tell whether these two graphs are isomorphic or not? It's not easy at all. For example, for these four graphs, Peter graph only with 10 vertices and then 15 edges, it's not easy to see that they are isomorphic. Actually, not easy at all. All right. So how can you tell that this graph is actually the same graph as this one? In fact, the problem to tell whether two graphs are isomorphic or not is not likely to be polynomial time solvable. As the best algorithm was obtained 3 years ago, it's in 2017 by Harvey. Its running time is still exponential, but it's not very bad. Running time is n to the power of say maybe in this way. Okay. So these two are constants. The running time something like this. So this one is same as not exponential function. So that's running time is something like this. Exponential function typically this part is order of n. Now this one exponential part is much smaller than n. Is probably log n. It's a polynomial function of log n. So it's much faster than this type of function. And be also lower than this type of function. The algorithm runs much faster than 2 to the power n. So that's the best we know. Right? So that's, I think this should be enough to give you the idea of graph isomorphism. It's very useful to compare this with the system linear equations to give you a better understanding what it means by graph isomorphism. Okay. So it's a reordering of vertices. It's a permutation of vertices. After this permutation, once we apply this permutation, then these two graphs look exactly the same in terms of the matrix or in terms of drawing in this linear way. Then these two graphs should look exactly the same. All right. So I will give you a very simple theorem about graph isomorphism. Graph is self-complementary if graph is isomorphic to its complement. All right. So for example, P4 apart from four vertices. So that's P4. All right. It's complement. It's a complement. It's a complement graph contain edges not in this graph. So that's the graph we get. So if I take it out, the graph look like this. So of course, this one is exact same as a P4. So one goes this way. So therefore, P4 is isomorphic to its complement. So P4 is self-complementary. Similarly for C5, right? So I have C5 cycle with 5 vertices. Now it's complement. Actually, it's the middle thing, this middle part. This is complement. All right, if I take it out, this complement look like this. Which is isomorphic fit to C5. It's easy to see. This one is just different drawing of C5. So therefore, C5 is isomorphic to its complement. All right. So this small result give you a necessary condition for a graph to be self-complementary. All right. Then we have a restriction on number of vertices. Number of vertices either multiple of 4 or 4k plus 1. Only two possibilities. And the proof is very, very simple, actually. So here is how proof goes. Right? So we know that the G is isomorphic to its complement. So what it means is number of edges of G is same as number of edges of G. So this one denotes the number of edges of this one. Okay, so M bar equal number of edges. When two graphs are isomorphic, they have same number of vertices, same number of edges. So we have this one. All right. So however, we know number of edges inside G plus number of edges is complement equal total number of edges on complete graph. So that will be n choose 2. This total number of edges. All right. Now 2m. From here we know 2m equal this one. So that gives us m equals n minus 1 divided by 4. So in order to be divided by 4, so here one is odd number, one is even number. Okay. So either n is divided by 4 or n minus 1 is divisible by 4. Either 4 is divided n or 4 divided n minus 1. There are only two possibilities. So that gives us this one or this one. All right. So in order for a graph to be self-complementary, the number of vertices must be a multiple 4 or multiple of 4 plus 1. So that's a very small result. All right. Okay. Yeah, it takes more time than I thought. Initially, I thought just 10 to 15 minutes about isomorphism, but I think it's the concept is very important. So I think it's worth give half an hour more to give you the idea connected to graph isomorphism, because this notion is really essential to graph theory. So I really want you to have a full understanding of the meaning of graph isomorphism. Okay. All right. The next thing we will do is to walk along graph. One nice thing about the graph is we can really walk along in the graph, like walking along edges. So what we'll do is walk along edges. So that will allow us to walk along these vertices and edges. So suppose I start with the vertex. So I can walk around, treat each edge as a street. I can walk around and walk around. Now, the only restriction is I cannot stop in the middle. I have to use the full edge. All right, I cannot walk here and then return. That's not allowed. When I walk along the edges, I have to walk along the edge until I meet another vertex. Then I can decide what to do. So I cannot stop in the middle. Because remember, graph is discrete. Okay, this edge, I have to use the full edge or not. I cannot use half of edge. All right, so that's only restriction. I can walk around. So once I get, then I can determine whether I can go this way or that way or that way. Does not matter. I can even turn back. Then go forth, and so on. So it's really like walking around. All right. So graph allow us to walk around in a graph, all right, along edges. So then we have a definition of a walk. So using this idea, we have definition walk. So walk is not for cooking, okay. All right. So we have a definition of a walk. A UV walk means I walk around starting from U and end at B, along edges. It's just called a UV walk. All right. So mathematically, it's a sequence. Let me see. I start with 0, 1. I forgot whether I start with 0, 1. No, a 1. Okay. That's a sequence, alternating sequence of edge and vertices. So that's why it's alternating. All right. Of course, I start with U, so U will equal V1. I end with this one. So that one is V. So this one is V. This one is U. It's an alternate sequence of vertices edges, so that each edge, so each edge connects the previous vertex with next vertex. So here will be V3. All right. So for example, E2 is exactly V2, V3. So it connects them. This is called the walk around. All right. So let's see a small example. For example, I can walk around like this. All right. So this red one walk, is a sequence consists of V1, E1, V2. So that corresponds to this section. Then V2, I go to E2, then V3. Then come back, again E2. Remember, UV is same as VU for undirected graph. Yeah. For direct graph, it's different, but for undirected graph, these are same. So here E2, then V2, then E4, V4, then E3, V3. So this is the red one. This is walk. All right. So start with this one and end with V3. So that gives us V1, V3 walk. All right. Now for walk, number of edges involved is called the length of walk. So here. The number of edges involved is called the length. So here is 1, 2, 3, 4, 5. The length of this walk is involved in edges. Some edge will be counted twice. So here E2 is counted twice. So 1, 2, 3, 4, 5. The length is 5. It's not a 4. Different edges is 4, but number of edges in the walk. Some edge will be counted more than once. All right. So that's the length. When all vertices in a walk are different, then we get a path. If we do not repeat vertices at all, then we get called a path. Sometimes we say it's a simple path. To emphasize no vertices are repeated. When no vertices repeated, of course, edges will not be repeated. All right. So that's called the UV path. So it really look like paths. So that's why we use this name. All right. So for example, here is U, here is V. So then it really look like paths. I cannot repeat it. I cannot repeat it. For example, this red one is a path. So you see no repetition of edges, no repetition of vertices. So it's really look like a straight line. And that's why it's called a piece. So here again, number of edges involved is the length. So 1, 2, 3, 4, 5. So here length is 8. Okay. All right. So that's very important and very basic notion. We can walk around, so we have peace when we do not repeat verses. And we have the following very important notion of connectedness of a graph. Like I give you two graphs. That's one graph. That's G1. Here I have a different graph. That's G2. Supposing that's G2. What's the difference between these two graphs? It's easy to see that's one piece. So here are two pieces. But in geometry, this one is called the connected graph. So this one is not connected graph, right? So that's one piece. That's more than one piece. So when the graph is one piece, then it's connected. But when it's more than one piece, then it's not connected. And mathematically, how can we define it? What do we mean that a graph is a connected graph? So mathematically, it means For every pair of vertices, there is always a piece between U and B. That's what means by connected graph. So this one, regardless of which two vertices we pick, we can always find a piece because it's connected. So we can always reach from one vertex to another. So this one means regardless which two vertices we pick, we can always reach from one vertex to the other. This means the path is connected. But this one is not. If U is here, B is here, there's no way I can reach from U to B by following a path. So that's a major difference between the connected graph and disconnected graph. So this definition of connected graph. Otherwise, the graph is disconnected. All right. So that's connected graph, and this one is disconnected graph. Now, you may say, okay, so this graph is disconnected, but each piece is connected. So this piece is connected, this piece is connected. Such each connected piece is called a connected component. So each connected piece is called a connected component. So each piece is called a connected component. All right. Now, how can we get unconnected component? Again, I cannot say each piece. What do we mean by each piece? So we can use binary relation to define connected components. So here I will give a connection between binary relation, equivalence relation. What we do is we define equivalence relation. Define a relation on vertex set. Right. So two vertices, U and B, will be related if two vertices will be related if only if there exists a UV path in G. Now, this relation is an equivalence relation. Certainly, it's reflexive because for each vertex, of course, it always has path to itself, right? So it's reflexive. Secondly, if U and V are connected, of course, that implies V and U are connected. So there's symmetry. It's symmetric, right? The thirdly, it's transitive. If U can reach V and V can reach W by paths, so what we have is here U, V, W, U, V, W. So we have paths, here paths. Now, these two paths may have something in common, right? But not yet. Whenever there are more, I can take this one. I can take a shortcut to find a path from U to V, U to W. This one is no application of vertices. So that means that relation is transitive. So this relation is a transitive relation. Actually, it's a reflexive, symmetric, and transitive relation. Therefore, it's a equivalence relation. So this relation is equivalence relation. All right. So what we know about equivalence relation, it has equivalence classes. Right. Now, equivalence classes exactly correspond to connected components. So each equivalence class gives us a connected component. So in this graph, so this equivalence class, this is another one. So there are two components. All right. Okay. Now it looks very easy to tell where the graph is connected. And once it's not connected, it's easy to tell how many components it has, right? If I give a drawing, For example, this graph, it's easy to see it's not connected, and it has three connected components. That seems maybe easy, but actually it's not easy to even tell whether a graph is connected. Algorithmically, it's easy, it takes linear time, but it's not straightforward. The reason it's easier to tell here because of the way I draw it. If I draw it in this way, each component is clearly separated from other components. I can draw it different ways, and it's difficult to tell when it's connected, and when it's connected, not connected, it's hard to tell the number of components. For example, I can give you the following graph. Just good enough, okay? For example, this graph, if I draw it this way, so you see my idea. It's not easy to tell whether this graph is connected or not. Now, when it's not connected, it's hard to know the number of components. There's this magic way to find it out. This one may have two or three components. I don't know. I cannot like this one. I can tell immediately, but for this one, I cannot. Okay. Okay. I think I should stop here. It's over a few minutes. Next week I will continue. Okay. I will discuss something more interesting. So these are very big things. Eventually, we'll have to get something more deep. And graph theory will really show the beauty of discrete math, also the difficulty of discrete mathematics. So on Monday, I will give you one example at least to show the power of graph theory and the beauty of graph theory when we use it to solve problems. It's really unexpected. Okay, so tomorrow tutor will discuss solution for homework 4. So tomorrow the actually because of convocation, class are suspended, but online will not matter. If you have time, you join. Otherwise, you look at the recording. Okay. So tutor will talk about solutions. As I said last week, because we don't have tutorial last week, so shift to this week. All right. Okay. So that's it for today. Homework 5. There will be one more homework. I think I will delay for one more week. Next week, I will give you homework 5. All right. That will be last one. All right. Also, one thing about the final exam, it's face-to-face for students in Hong Kong. My understanding is students currently in Hong Kong or at time of exam, they are in Hong Kong, they should come to university to take home face-to-face exam. Otherwise, I think it will be online. Details, I think, will be decided by yes. Okay. All right. So see you next Monday. Bye-bye. Oh, Lisa party, it's hard to say right now. Uh, Normally, I think it's around the 50, right? Should not be, if you're above 50, normally you will be guaranteed to pass somehow. I'm not 100%, it's all depends, all right? So usually it's 50 or a little bit lower. Or update, or you haven't got updated. Uh, I think, okay. Actually, it's very easy to tell because the only problem with marking in Q4, you can easily tell. So they marked uh, AB as 0.5 marks. So if you are correct, you just add one. All right, something like that. Okay. Oh yeah, yeah. Can be a lot of UU paths. Yeah, yeah. Between any two verses, there can be many, could be many different paths. UU path may not can be a trivial path of length 0. UU path has length 0 because it involves no edges. But there can be other UU paths to get a cycle. In that case, you'll get a cycle. I haven't defined the cycle yet. Okay, any other question? One is not possible. You're right. Yeah, one is not possible for you pass. Yeah. Yes, I have two, at least two, or there are at least two. Yeah. Yeah, the trigger case, a walk can contain zero edges. Then it's a walk out length zero. So a kind of boundary situation. Okay.